Welcome back to our series on electricity and magnetism. In this episode, we're going to begin our exploration of the magnetic field. Magnetic fields are related to, but very, very different from electric fields. Our most familiar relationship with a magnetic field is through experimentation with a permanent magnet. And this is something we've all done throughout our lives. We've sort of played around with the magnetic force. A permanent magnet features magnetic field lines that radiate out of the north pole of the magnet and towards the south pole. And that's the way in which electric and magnetic fields are similar, in that they both have a certain polarity to their fields, where the field lines run in predictable ways. But that's really where the difference ends. You'll notice that the magnetic field lines run from north to south, and then they run through the magnet back to the beginning of the field line. That is, the field lines themselves run in complete circles. In the same way of electric field lines, the density of field lines is an indication of field strength. So you can see the field is particularly strong near the poles. But as you get further away, particularly along a line perpendicular to the magnet, the field weakens significantly. Strong magnetic fields occur very near the poles, but the field lines run in full circles, and that gives you a little bit of a clue on how different magnetic forces are from electrical forces. Of course, we can use this configuration slightly differently. I can take two magnets and put them end to end so the north and south pole are very close to each other. A picture like that would look like this. So we have the north pole and then the south pole of a separate magnet close by. This, of course, is still going to produce field lines that run from north to south, but now we'll get a relatively consistent field that has equal magnitude throughout, indicated by the parallel field lines. Well, how do we designate a magnetic field? Well, we use the capital letter B, and that sort of represents the same thing as the capital letter E does for electric field. It represents the strength of the field. It's a vector field, so it represents both the direction it points as well as the strength of it. Well, we learned about electric fields by first looking at the Coulomb force between charged particles, and then we used that to develop this idea of a field. And you might think it's strange that we're jumping straight to the field idea with magnetism. Where's the Coulombs Law equivalent? Well, let's write it and see what it would be if it existed. The force due to a magnetic field should be proportional to some sort of amount of magnetic north pole particle, an equivalent amount of magnetic south pole particle, the product of those, divided by the radius between them squared. That is, the strength of the magnetic field goes according to Coulombs law. The only problem is there's no such thing as these magnetic particles that represent the magnetic northness of the electric or magnetic field and the magnetic southness. These would be called magnetic monopoles, and although scientists have looked for them for centuries, they don't appear to exist. That can be proven because if we snap this magnet in half, we simply get two magnets with a north and south pole. And if we snap those in half, and then in half again, and again, and again, no matter how small a particle of a permanent magnet I have, it still has a north pole and a south pole. There's no way to divide the northness from the southness, and there's no particle responsible for that northern property and southern property, which is why we will never have a Coulombs law style magnetic force. The magnetic monopoles simply do not exist. So how do we go about measuring the force that magnetism causes? Well, it turns out that magnetic force only exists really between magnetic fields and other magnetic fields in the case of permanent magnets. But the other place we see it is we see a magnetic field have an influence on a charged particle, but only if it's moving. Suppose I had a uniform magnetic field. So this represents a B field similar to what we would have in between the poles of a north and south pole magnet held close to each other. Well, now let's take a charged particle and have it travel through this field. That is, I'm going to take a positive particle and I'm going to have it travel through the field with a velocity. Well, as we can see, the vector velocity is going to interact with the magnetic field, and it will actually cause a force on this charged particle. That force is based on the magnitude of the velocity, the magnitude of the charge, the magnitude of the B field, and it turns out to be a cross product. So it has everything to do with the sine of the angle between the velocity and the magnetic field. That's going to be this angle right here. So the force due to the magnetic field on this charged particle, as I said, is a cross product. It's QV crossed with B. And if you recall, a cross product measures the degree to which two vectors are perpendicular. The more V and B are perpendicular, the larger will be the magnetic force. So the magnetic force is greatest on a moving charged particle if it travels perpendicular to the field. And that's kind of counterintuitive. After all, magnetic forces, electric forces existed between stationary charged particles. And the direction didn't really matter. It always was attractive. But this force is actually applied both perpendicular to the direction of the velocity and perpendicular to the direction of the field. Remember, we can use the right-hand rule to work this out. And the way you use the right-hand rule is using your right hand. What I want to do is first direct my thumb in the direction of the velocity. And then I want to move my fingers so that they are in the direction of the magnetic field. So that thumb in the direction of the velocity, fingers in the direction of the field. Now if I curl the fingers of my right hand forward, that will point in the direction of the force. In this case, that force is directed in this direction, perpendicular to both the velocity and the field. Because for me, that's going into the board towards the camera. We'll need to come up with a way to draw that. After all, this is a flat drawing, and I want to indicate a force in that third dimension. So an easy way to do that is to draw this symbol. It's a circle with a dot in it, and that kind of looks like an arrowhead coming at you. That would represent something that's coming towards you. And then a circle with an X in it kind of represents the tail feathers of an arrow. It looks like it's going away from us. So this would represent away. And from my perspective, using the right-hand rule, thumb, fingers, direction towards the camera, that means it's moving away from me. So the force at this location, FB, would actually be directed on that particle, and it would be directed into the board towards the camera. So this is how we calculate the size of the magnetic force. And although it seems unusual, magnetic forces are inherently unusual, very different from electrical forces. If there isn't relative motion between a charged particle and the field, then the magnetic force will be zero. If I simply placed the charged particle in the field, it wouldn't move at all. Because the cross product can be calculated where if all we're interested in is the magnitude of the force, not its direction, remember we can drop the cross and add in a sine theta. So it would be QVB times the sine of the angle between them. As you can see, as this angle gets smaller and smaller, the velocity of the particle will get more and more parallel with the field. When the velocity is parallel to the field, the magnetic force disappears. It has to be moving across the field in some way. Perpendicular is best, but parallel produces zero magnetic force. Magnetic fields actually originate from moving charge, but we won't look at the source of magnetic fields until later. Until then, we will look at the impact of the magnetic field on moving charges. That turns out to be one of the greatest applications of the magnetic field. It's a great way of controlling the movement of charge.